Engine power must be converted to useful power by controlling speed, direction, and force. Transmissions do this by either hydraulically engaged planetary clutches or hydrostatic hydraulic drive. Each of these methods has different characteristics for ground speed, torque, clutch maneuverability, and implement force. Direct drive transmissions use mechanical gear trains to control speed, direction, and power from the engine through the drivetrain. A direct drive transmission receives engine torque through a flywheel clutch that gradually engages the engine and transmission. The flywheel has three parts. The driving plate is splined to the transmission input shaft. The driven plate is splined to the driving plate, which also connects it to the transmission shaft. When it turns, the transmission shaft turns. The driving disc between the two plates is splined to the engine flywheel and rotates at engine speed. When the clutch is disengaged, the driving and driven plates are idle, with the driving disc rotating at engine RPM. When the operator shifts into a gear and engages the clutch, a cam link and sliding collar mechanism push the two plates together with driving disc between them. As friction increases, the engine power in the driving disc begins to rotate the plates, turning the transmission shaft. When fully engaged, the disc and plates rotate as a unit.
Speed changes are made by engaging gears of different sizes. When the driving gear is smaller than the driven gear, output speed is reduced and torque is increased. When the driving gear is larger than the driven gear, output speed is increased and torque is reduced. When gears are the same size, force is simply transferred from the driving to the driven gear with no change in speed or torque. To move from neutral to reverse requires engaging three gears: the driving gear, driven gear, and an idler gear. An idler gear is located between the driving gear, driven gear, and an idler gear. An idler gear is located between the driving and driven gear and is used to change the direction of the output shaft's rotation. If we want to move in reverse, we want the output shaft, to which the sleeve of the driven gear is splined, to turn the same direction in which the input shaft is turning.
Direct drive transmissions are used in work needing few gear changes. An example might be a Challenger ag tractor as it works in the fields. The advantages of direct drive transmission are low initial cost and low repair costs. Power shift transmissions change gears and speed under load, allowing full power speed and direction changes. Smooth shifting reduces operator fatigue in frequent shifting applications. Planetary power shift transmissions are made up of planetary gear sets that work similar to the way planets revolve around the sun. Any members of the planetary set, the sun gear, ring gear, or planet carrier, can be stopped by hydraulic clutches. When the clutches are disengaged, the sun, planet, and ring gears rotate as a unit. But when the clutches are engaged, they stop one of the members of the planetary set. Combining planetary gears into a power shift transmission provides the required number of gear ranges and forward-reverse speeds to match the machine application. The name countershaft power shift transmissions comes from adjacent shafts that run in opposite directions and counter each other. All gears are in constant mesh. Like power shifts, they can make speed changes under full load. Operator controls actuate speed clutches that connect various gears. Direction is changed the same way, using directional clutches. These are larger and contain more friction discs and clutch plates because of the higher energy they transmit during direct. The hybrid planet. The name countershaft power shift transmissions comes from adjacent shafts that run in opposite directions and counter each other. All gears are in constant mesh. Like power shifts, they can make speed changes under full load. Operator controls actuate speed clutches that connect various gears. Direction is changed the same way, using directional clutches. These are larger and contain more friction discs and clutch plates because of the higher energy they transmit during direction changes. The countershaft transmission has fewer parts than planetary transmissions, making repair and service faster and cheaper. The hybrid planetary countershaft transmission combines the high torque multiplication of the planetary transmission with the minimal shifting of the countershaft transmission.
It is used in the Challenger 65, 75, 85, and 95 ag tractors, and the 14H and 16H motor graders, machines whose work involves long operation in the same gear. During shifts, the clutch action
demand. Hydrostatic transmissions facilitate power turns, counter-rotation of track for spot turns, automatic speed control, and load compensation. The hydraulic flow may also be directed to run machine implements or auxiliary equipment. Because of these qualities, Caterpillar uses this type of transmission in the D3C, D4C, and D5C track-type tractors, the 902 through the 914 wheel loaders, and the 953, 963, and 973 track-type loaders. In hydrostatic transmissions, mechanical engine power is converted to hydraulic power. This hydraulic power is then converted back to mechanical power by a piston motor in the final drive of each wheel or track. Unlike other types of transmissions, hydrostatics have no mechanical drivetrain parts. The engine drive shaft provides power to drive two piston pumps and a gear pump. The piston pumps deliver a varying flow of oil to the piston motors that drive the wheels and control their speed. To turn the machine, pump flow to one motor is decreased, which slows its wheels and causes the machine to turn in the direction of the slower wheel. These pumps and motors are bidirectional to allow travel in both directions. The gear pump supplies oil needed to operate the system and dissipate heat. Cat 416 through 436 backhoe loaders, both 2- and 4-wheel versions, use power shuttle transmissions. This type of transmission is manually operated, is synchronized, has a 4-speed direct drive arrangement featuring constant mesh helical gears and hydraulically shifted forward and reverse shuttle clutches. Direction and travel speeds can be changed on the go through all gears via electro-hydraulic forward and reverse shuttle clutches. A synchronizer assembly assures that the input shaft from the torque converter and the clutch plates are rotating at the same speed when engagement takes place. Gear changes are smooth without losing load-carrying force or ground speed. A freewheel clutch in the converter allows the stator to freewheel during high-speed, low-load situations such as roading. A large-capacity torque converter applies engine power efficiently, and a low second gear ratio provides high rim pull for outstanding lugging ability.